So is this the one that you told me has like a big difference between that and the right side?
All right. Now we are going to start with the Newtonian laws. The first Newtonian law: an object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an outside force. This is also known as inertia. Inertia. An object wants to keep doing exactly what it's already doing. It doesn't want to change.
No, really.
All right. Right here on the floor, I have a bowling ball. Now everyone look at this bowling ball. Is the bowling ball moving?
No. Should I kick it? I'll volunteer.
Okay. Stop. The bowling ball is not moving. Now, inertia says it won't move. Now watch it. Is it moving yet?
No.
Is it moving?
No.
Has any force acted on it?
No.
And it's going to stay not moving as long as we don't have a force. But wait. If I add a force. Oh, the ball's moving. There it goes. Let's keep going. Boom! It keeps moving until acted upon by another force.
Well,
friction is another force.
So we just saw the ball at rest stayed at rest. Once we put it into motion, it stayed in a straight path until it hit the chair. So it will continue in the same exact path until an outside force acts on it. It makes it change. So basically, an object is going to keep doing the exact same thing until something stops it from doing that.
What does inertia depend on?
That's a great question. What does inertia depend on? Inertia depends on mass. Inertia is completely dependent on mass. When mass goes up, inertia goes up. When mass goes down, inertia goes down. Right here, example. Is it easier to move that wheelbarrow when it's full of dirt or when it was empty? Empty. It's much easier to move when it's empty because it has less inertia. All right, let us continue. An example again. In a car accident, what happens to the person not wearing the seatbelt?
They die.
All right.
Shards of glass inside your
Quiet. So this person is in motion. They're going 45 miles an hour down the road and then crash. Now, as soon as they make that crash, that person is still going 45 miles an hour. And they're coming out of the seat. They're still going 45 miles an hour. Still coming out of the seat.
But when they hit the glass?
And then they're going to hit something. Maybe they hit the side of the car. Maybe they hit the windshield. They're going to keep going until something slows them down or stops them. So yes, inertia is going to cause them to continue moving forward until something stops them. That something could be the windshield, could be the dashboard, could be the road.
Whoa.
I know.
Or a train.
I guess it could be a train. You're right. All right. Next example. Okay, this one's a tough one. First period kind of messed this up, so pay attention. The astronaut pictured right here wants to push something, that screwdriver. That screwdriver has less mass. What is going to happen? Let's watch. Oh my gosh, the screwdriver moves away. Did you see that? Can you believe it? I believe it. The screwdriver had less mass, it had less inertia, so it took off.
I get it.
All right, next example. Same astronaut, but he's going to try to push the space shuttle out of the way. Okay. He is now going to push the space shuttle out of the way, and here he goes. Oh no, he went out of the way.
No, he pushed it.
That'll
It's just
suck.
camera pan.
If you're like floating down to space.
That's what.
All right. So the astronaut, because it had less inertia, the astronaut, he is the one that moved. All right. Now we're on to the second Newtonian law. Second Newtonian law says the acceleration depends on mass and force. We talked about this formula the other day. Right here. We have a man pushing another man on a tractor.
I feel the tractor's a little small.
Now, is this possible? Can the man add a force there and push it and make that tractor accelerate? I bet he can.
This way. Just stop, Grayson.
Now, we're going to change it. I'm going to change the variables just a bit. What about pushing your elephant?
Your friend's pet elephant. Oh.
We changed the mass just a bit right here. Do you think the elephant has enough inertia to keep from being pushed around? So the elephant does have a lot more mass. Because it has more mass, it has more inertia. Because it has more inertia, he's not pushing it. Newton's second law. We have a formula to go with it. So the formula that we talked about yesterday, F equals ma. Force equals mass times acceleration. F equals m times a. Whoa, buddy. There we go.
F equals
All right.
A.
F equals m times a. Mass times acceleration. It's good stuff. Now when we calculate this, and we are going to be doing some math problems with this. First thing, we have to make sure we're using the correct units. Mass has to be in kilograms. Acceleration has to be in meters per second squared. Force is in the Newton. So our example right here, how much force would it take to accelerate a 22 kilogram girl on this swing? We want this girl to accelerate at 3 meters per second squared. So what I want you doing on problems like this, first thing I want you to write down is the formula. Our formula is F equals m times a, so you write that down. So F equals m times a. Now you plug in the numbers. The mass that we're talking about is 22 kilograms. The acceleration is 3 meters per second. So there's the numbers. Now you know in the STAR type test you are not going to get a calculator, so you're going to have to work this out.
That sucks.
You can either do this in your head or you can write it on paper. Do it now.
I think 66.
66, and our unit is the Newton. Example number next. We have a weightlifter lifting some weights. He wants to lift 240 newtons of force. He wants it to accelerate at 10 meters per second squared. What is the mass that he's lifting? First thing you have to do, write the formula. Second thing you have to do, substitute in the numbers. Third thing you do, solve it. Go, go, go. I want to see answers on your paper before I put it on the board. All right, I just walked around. I saw most of you do have this. So we have the formula. Mass is going to be equal to force divided by acceleration. That's 240 divided by 10. If you look at this right here, anything that is identical on top and bottom can be canceled. That means the meters per second canceled. You can cancel out the zeros. When you cancel out the zeros, that leaves you 24 divided by 1. 24 divided by 1, last time I checked, was 24. Our unit, kilograms. Whoa. Now, example number next. All right. What would the acceleration of a 500-gram ball thrown with a force of 25 newtons, what would it be? Solve it, and I'll be around and finish it on the board in just a second. The first hint I'm going to give you, look at the unit for mass. The unit for mass, I gave you a unit in grams, but you must have this in kilograms. So you're going to have to convert from grams to kilograms before you can solve anything else. So yes, 500 grams is equal to 0.5 kilograms. There are 1,000 grams in a kilogram. You do the math, you divide it out, that's 0.5 kilograms. So now here's our formula. Plug in the numbers. 25 divided by 0.5. When you divide by 0.5, that's the same as multiplying times 2. 25 times 2 is 50 meters per second. There we go. Continuing on. Humpty Dumpty sat on a wall. Humpty Dumpty had a mass of 1.5 kilograms. I want to know what force he hits the ground with when he accelerates at 10 meters per second squared before his great fall. There we go. So, you know the variables. You know the formula. Solve it. So the mass right here is 1.5 kilograms. The acceleration is 10 meters per second squared. You multiply these two numbers, you're going to get 15 newtons. That is right. Friction. You asked me about friction earlier. Friction. Friction is a force. Friction is a force that is caused by motion. The entire purpose of friction is to stop that motion that caused it. For example, we can have fluid friction. If you look at this leaf falling down, that is a fluid friction. The air is slowing it down. You can have water and oil. Any of these things are fluids. You can have rolling friction. This is with a wheel or a ball. You can have sliding friction. That would be like trying to drag the desk around the room.
Wait, is air fluid?
Yes, air is a fluid. Newton's third law. The third Newtonian law. Third law states, for every action, there is an equal and opposite reaction. Action, reaction. Basically what it says is all forces come in pairs. No matter what, there's always going to be another matching but opposite pair. Need proof? So, I know some of you in here are hoop stars. It is hoops season right now. You're going around, you're dribbling that ball, you slam it against the court, and what does that basketball court do?
It moves down.
It does move down a little bit, but then it hits the ball back towards you. Equal and opposite. It's true. I've seen it happen.
Or when you walk.
Now, think about this. I'm walking around the room right now. I'm moving forward when I walk. But to do that, what do I actually have to do?
Use friction.
Which way am I pushing to make myself move forward? I push backwards when I walk, but I move forwards. Equal and opposite. For every action, there is an equal and opposite reaction. So we do know that. Example. Why do boxers wear gloves? It's not to protect the guy they're trying to beat up. It's to protect their hand. They're hitting a guy in the face. And if they don't have this glove to protect their hand, they're going to break their hand.
Yeah, I'm gonna break your hand on your face if you don't mind.
Grayson.
We've all seen old movies. Watch this. He shoots. And the guy flies away. But that's not how it would really happen. Oh no. It would not really happen like that. If there was enough force to knock the evil guy away, it would actually knock them both away. Because it's equal and opposite. Okay, quiet. Let's go back to our example from earlier. We have an astronaut and a screwdriver. We already saw that the astronaut can push that screwdriver away. But we just learned that there is always an equal and opposite reaction. So here we go. The screwdriver moves away quickly. The astronaut moves away slowly. We have the astronaut and we have the space shuttle. If the astronaut pushes the space shuttle, will it move? No. Yes, but slowly. All right. Have an amazing night. See you all tomorrow.